Hi folks, we're going to take a look at the solution to page 53, number 15. Okay, so a bit of a different question. So they're asking us to determine what's true about the values a and b so that this function f, that is a piecewise function, is continuous at x equals 1 but discontinuous at x equals 2. Okay, so this is what we're trying to determine conditions on, and these are the givens. Okay, so in order for this function to be continuous at x equals 1, we're going to need the limit of f at x as x approaches 1 from the left to be equal to the limit of f at x as x approaches 1 from the right. Okay, and of course the limit has to be equal to the function value, but I notice here that it's actually defined at 1 to be exactly equal to that expression. Okay, and so that'll be taken care of. So main thing is to determine the conditions on a and b that are going to make this equation true. Okay, so let's find the limit as x approaches 1 from the left. So in this case here, since we're approaching 1 from the left, we're using this expression to represent the y values. So ax minus b over x minus 2. And when we're approaching 1 from the right, we're using this expression to represent the y values. Okay, now the fact that past 2 it has a whole different equation doesn't really matter because we're only looking at approaching 1. So we're looking at near 1 on the right hand side. So the 3x will do that. Okay, now these are both fairly nice functions. Okay, because while this does have a vertical asymptote, it doesn't have an asymptote at the value at which we're approaching. Okay, so if we think of it, even in terms of, our limit properties, since the limit exists for both of them, I could take the limit of the top and divide that by the limit of the bottom. Okay, so here, what does the top approach? So ax minus b, well, as x gets closer to 1, this is just going to approach a minus b. And x minus 2 is just going to approach, well, 1 minus 2 is negative 1. Okay, and on the right hand side we again have a nice function, just a polynomial function, so we know that it has a limit everywhere. So the limit of 3x as x approaches 1 is just going to be 3 times 1, 3. Okay, and what this first condition gives us is a condition on a and b. Okay, so a minus b has to be equal to negative 3. So that means there's infinitely many values of a and b that are going to make this function continuous at 1. Okay, so this is the condition we have to meet. Okay, if I want, I can even rewrite it. A has to be equal to b minus 3. Okay, so if I pick a b value, the a value is automatically given by b minus 3. Okay, but now we have to meet the second condition. This is where the question's a little different because they're not asking it to be continuous at x equals 2. They're asking it to be discontinuous at x equals 2. So that means the limit as x approaches 2 from the left, okay, has to not be equal to the limit as x approaches 2 from the right. Okay, so let's figure out what has to happen in order for these not to be equal. Okay, so again, if I'm approaching from the left here to the left of 2, I'm going to be using 3x. Okay, and that has to not be equal to the limit as x approaches 2 from the right, so I'll be using bx squared minus a. Okay, so this limit here we've already determined as a sorry, we haven't determined this one. We determined as x approaches 1, but it'll be the same when x approaches 2. So this is going to approach 3 times 2, which is 6. And that can't be equal to, and again, this is just a quadratic, nice function, has a limit everywhere. So this is just going to approach b times 2 squared minus a. Okay, so in other words, 6 cannot be equal to 4b minus a. Okay, so these are the conditions on a and b, okay, in order to satisfy the second condition. Okay, so here I guess we can write this as a cannot be equal to 4b minus 6. Okay, so these are the two conditions that we have to meet in order for this to work out. Okay, so what this tells us is there's likely infinitely many solutions. Okay, we can even go a little further, and we can do a little solving here, is if we say that A can't be equal to 4B minus 1, 4B minus 6, well, we also know that A has to be equal to B minus 3. Okay, so this A value can also be written as B minus 3. Okay, and so now we can solve this here. So this is just going to be 3B cannot be equal to negative 3 plus 6 is 3. Okay, so B can't be equal to 1. Okay, and so that means A, okay, based on the fact that A is always equal to B minus 3, those are the only values we're looking at, can't be equal to 1 minus 3, which is telling us that A can't be equal to negative 2. Okay, so this condition must be met. Okay, however, we can't use the value 1 and negative 2, which would satisfy this expression, okay, but then would contravene this necessity here, which is that A cannot be equal to this expression. Okay, so to recap this question, okay, number one is to understand that when a function is continuous at a point, okay, it means that the left-handed limit is equal to the right-handed limit, and those are both equal to the function value. Okay, and in this case here, where they want it to be discontinuous, it means that those two limits are not equal to each other. And from there, we were able to set up this system of equations which had infinitely